Hello, all of you. We'll wait for some time and then we'll start our session. As we know, we are this is our ninth session on the study guide in the organic retrosynthesis, a problem-solving approach, and we have covered most of the concepts based on the retrosynthesis, and now we have slowly moved toward the uh, asymmetric synthesis. So. In the particularly asymmetric synthesis, so we have already the first thing that we have covered about the resolution method. Sure. For resolution for the purification of the compounds, particularly the enantiomers or the diastereomers, and then after that we have seen some examples of the chiral pool synthesis. So this is the one example that I have given you for the homework. So we'll solve that question and then we will see how uh, the chiral pool synthesis has been done to synthesize this L-lysine. So this is basically the non-essential and L-amino acids. So the chiral pool synthesis of the essential amino acids uh, L-lysine from the natural non-essential uh, L-serine has been achieved in this synthesis. So basically, this is the L-serine, the structure of the L-serine. And when you do the CBZ protection on the L-serine, so the CBZ attack on the NH2 group, so N-CBZ protection has been takes place. Then when you do the DCC reaction of the alcohol with the DCC, it will be a esterification reaction. So the ester group form here. And when we do the oxidation by using the pyridium chlorochromate, we can selectively stop the oxidation of this primary alcohol to the aldehyde stage. And here we get the aldehyde. So once the aldehyde is achieved, so then when we treat this aldehyde with the Wittig salt, so upon treating this aldehyde with the Wittig salt, Wittig reaction takes place. And generally in the Wittig reaction, as we know, the from the unstable Wittig, so we get here the uh, E isomer. So in this case, also we got that E isomer, and anyway, whatever whether it is E isomer or Z isomer, at the end we need to reduce that olefin. And so up to here, this is the Wittig reaction. So in the Wittig reaction, the aldehyde functional group converted to the corresponding double bond and CH2 C triple bond N group. So basically, this step takes place in the Wittig reaction, and when you do the H2 PDC reduction, so the double bond is get reduced. So this is about the synthesis for this L-lysine. So this is L-lysine is the one of the essential amino acid, and this can be synthesized from the natural non-essential amino acid. Then the next example here is the based on the same chiral pool synthesis, which involves some functional group interconversion. So this is the chiral pool synthesis of the essential amino acid L-lysine from the natural non-essential amino acid L-serine can also be achieved. So basically here, whether it is same or different, I'm not sure exactly. So okay, we'll look step by step. Whether it is the same approach or the different, we'll see that one. So first CBZ protection, so that's the reaction, followed by the esterification, and then oxidation of this alcohol using the pyridium chlorochromate to give the aldehyde. So was the aldehyde form? The Wittig reaction followed by the H2PDC reduction. The same example, I just repeated. So we will not gonna look that one. Okay. So this is another asymmetric synthesis using this chiral pool asymmetric synthesis approach. And in this example, you can see, so our product is the L-alanine. So basically this NH2 group directing upward. And so if you look at the configuration of this group, so this will be 1, 2, 3, this will be the S. And since the, sorry, so this will be a S configuration, right? It has the S configuration. And when we look at the how the asymmetric synthesis for this L-alanine has been done here. So the first step here is the esterification reaction using the DCC coupling reagent and the benzyl alcohol. So once this benzyl alcohol, so this is the here the first reaction is the similar esterification reaction which earlier also we have seen. So the esterification reaction, okay. Then the next step is the, if you look closely at the reagent, so the reagent is the PPH3 and the I2. So basically here this step is the SN2 reaction, and the in this SN2 reaction, so the inversion in the stereochemistry takes place. So if you look at here, so the hydroxy group directing upward. Now in the product, the nucleophile, that is the iodine, which is directing downward. So basically this is the SN2 reaction. Earlier also we have seen the example of SN2 reaction. SN2 reaction is highly stereo specific reaction. So in the SN2 reaction, the configuration of the starting material and the configuration of the product are completely different. So when you start with the uh, so here when you start with the directing group, so the sorry, the leaving group, which is directing upward, so we are getting the new nucleophile which is directing downward. So this is what we get in the SN2 reaction. Not necessarily R changes to S or S changes to R. So because the R and S configuration, they are the relative configuration, right? So we cannot say directly whether if the how the compound, which is the, let's say here, this is the S and the product, yes, changes to R, product is R. So in this case, the starting was the S and the product is R. So, but this is not always the case. Okay. So the next here is the, once we get this product, so when you do the reaction with the NaN3, so this is again the second SN2 reaction, and the N3 nucleophile. So this is the plus and this is the minus. So this N3 nucleophile attacks on the center where iodine is attached. Now iodine is good leaving group, so it will be eliminated very easily, and N3 attack directly on the place of the iodine. Then in the next step, so when we do the H2PDC reduction, so the N3 get converted into the NH2. So the nitrogen get eliminated from the reaction, and we get here the NH2 amine group attached here. So this is basically our target molecule, which is the L-alanine. Okay, so this is the example, another example of the chiral pool synthesis. So do you have any doubt? Please let me know. We'll take some more example of the chiral pool synthesis, but right now, if time permits, I will take that examples later. But right now, we'll move toward the another third approach in this asymmetric synthesis, which is a chiral auxiliary approach, and this is one of the important approach. So generally, you may see some examples based on this approach. Okay, so what is chiral auxiliary? So the chiral auxiliary is a chiral molecular unit that can be temporarily, what is this? That can be temporarily incorporated in a chiral substrate to guide the selective formation of the one of the possible pair of enantiomers. So basically, this is a temporary unit, and you need to add that to the chiral substrate. So once we add this temporary unit or in the form of chiral auxiliary to the chiral substrate, so the reaction that we are going to perform on the substrate after adding which has the chiral auxiliary. So the addition of this new reaction or the reaction on this new substrate with the chiral auxiliary will be governed by the stereochemistry present in the auxiliary part of this compound. When you see actual example, then you will get to know in more detail. But here you can see here. So this is the example of the chiral auxiliary used in the alkylation of enolate. So if you look at this is the chiral auxiliary here, and how we can use this chiral auxiliary to the formation of the alkylation of this enolate. So that we will see in some example later. But how this chiral auxiliary work? So this is basically a chiral auxiliary physically blocks one of the two possible trajectory of attack. So let's say we have here, in this case, what we have here. So we have this substrate present here, let's say, which is in the form of, I will write down two different substrate. One is in the red and one another in the green. So then it will be easy to understand. So in this side, I have this starting. Now you can see if I want to attack the nucleophile attack on this side, how many different possible way? Either attack can take place from the bottom side. So what is possibility? The attack can be either from the top side, right? Or attack can be from the bottom side. So these two possible attacks are possible on the substrate. But if you add the chiral auxiliary on the substrate, so what happen? So the chiral auxiliary you can add instead of this hydroxy group. If we convert this compound in this manner, so the auxiliary part I will write down here with some different color. So let's say, so this is our chiral auxiliary, which has the like this some substituent. So, which has here some, let's say here the methyl group, and similarly here there is a, instead of methyl, let's say isopropyl group. So this is much more bulkier now, right? So let's say we have the isopropyl group, and here we have this R group is which is the, let's say the phenyl with the some R groups. So here also it will be the same phenyl with the R group, the two different R groups. So basically, I want to say here, so why I have drawn this with the R group. So mainly this part is the bulkier part. So whatever this part here also. So whatever the auxiliary part that we are adding, so the group present on the auxiliary will be oriented in this manner. And now when we do the reaction on the substrate, so this is again CS3, which is again from the starting. So so basically this is the overall the chiral auxiliary part that we have added on the same substrate. So on this substrate only, the substrate which is on the left. Now the auxiliary part is here. Now let's say the addition of the nucleophile. So if you look at here, so because of the steric bulk of this isopropyl group, the attack of the nucleophile from the top side, which is sterically hindered, and therefore the attack on the bottom side is more feasible, and we are getting here in this case the attack, the bottom side attack, right? And therefore the only selectivity will be the attack will be taken on the, here the selectivity is enhanced because of the steric hindrance of the chiral auxiliary, and the attack on the bottom side is only the dominant attack and the respective product we are getting in this step. So this is how the chiral auxiliary work. So that's what mentioned here. The chiral auxiliary basically physically blocks one of the two possible trajectory. So in this example, the two trajectory was attack on the either on the top side or the attack from the on the bottom side. So this was the two different trajectory possibles. So what the chiral auxiliary has did, chiral auxiliary block the attack from the top side, and therefore only attack on the bottom side is only uh, feasible in this case, and we can get the selectively attack on the bottom side, and this is respective product we get as a major product, or the we get the selectively the respective product. So this is how the chiral auxiliary works. So since this chiral auxiliary is enantiopure, the two trajectory are not equivalent but diastereomeric, and the temporary stereo center introduced by the chiral auxiliary direct the formation of the second stereo center, that is basically on this center. This is the new stereo center is generated. So we are getting basically a diastereomeric two different form. The stereochemistry of the new chiral centers can be rationalized by the steric consideration. So basically, the steric consideration, if it is higher steric repulsion is very higher in the chiral auxiliary. In that case, we can basically enhance the selectivity. So depending upon the what sort of how much the steric bulk we are using on these in this auxiliary, we are getting the selectivity according to that one. Sometime if we use the proper much bulkier group, so that the orientation of the chiral auxiliary takes place in such a way that the attack on the side of this chiral auxiliary is literally impossible. Then then in that case, what we get? We get a selectively attack on the opposite side of this chiral auxiliary. So this is how you can enhance the rationalize. Basically, we can enhance the selectivity by selecting suitable chiral auxiliary. So that's what he's here mentioned. We can basically rationalize this thing by the steric consideration in the chiral auxiliary. So if you look at the some of the example of this chiral auxiliary, so let's say chiral auxiliary approach, asymmetric enolate alkylation. So enolate alkylation of enolate that we already know. So I don't think we really need to discuss that one. We see the asymmetric version of that one by using this carboxylic. So optically active carboxylic acid can be prepared with the high enantiomeric excess based on the chiral auxiliary approach to asymmetric synthesis. So this is chiral auxiliary we have. So when you add the butyl lithium on this one and followed by the acyl chloride, so what happened? So this acyl chloride is prepared from the acid, propionic acid with the PCl5. So we get the acyl chloride. So that's okay. So we'll ignore the initial steps. So ignore these steps. Ignore these steps. Though our we have the acyl chloride here. Acyl chloride plus amine. What happened in place of butyl lithium? That is the base. This NH bond is basically proton from the NH get abstracted by the butyl lithium, that is the by the base, followed by the nucleophilic attack of this nitrogen on this carbonyl center to get the Cl elimination, right? And we get the amide formation here. So you can see here. So this is basically the amide new form amide. When you add the LDA, that is the base. So when we add the base on these, what happen? We have this acidic proton, which is alpha to the carbonyl group. So one of the proton from that one get abstracted and it forms this enolate, that is Z enolate. Why it forms the Z enolate? Because we get some six-member ring formation takes place by using the by chelation of this by using this lithium cation. The chelation occurs between the two adjacent. Uh, so these two oxygen atoms. So the base abstract the proton, it forms the anion here. So basically what happened, if I just show the step by step. So we get the anion at this position. Once this anion forms, this bond goes here and it forms O negative. So when it forms the O negative, what happened? So basically here we have this O negative and obviously there should be a sorry, the Li positive, right? Li positive is a counter anion. So this oxygen adjacent oxygen, this adjacent oxygen atom also participate in the bond formation, and it will we get the here the six-member ring formation takes place, and basically we get here the CH3 will be directing downward because the stable enolate we get in this case, right? Because there are two possibilities, either CC enolate or Z enolate. So sorry, the E enolate or the Z enolate. So in this case, so if you add the enolate in this form, let's say this CH3, this will be slightly unstable. Why? Sorry, slightly sterically hindered. But this inlet is a more stable inlet. So the Z inlet is majorly formed. So once this Z inlet formed, now let's see if we look closely at the this inlet. Now forgot about any all the reactions. Now only focused on these the form intermediate. Mm. So this is how we have the Z inlet. And if you look closely on the stereochemistry of this chiral auxiliary part, so the auxiliary part, so this is directing upward. Now, when we provide this electrophile, which is the pH CH2I, so this is basically delta positive, right? And this is delta negative. Now, if you look at here, the attack on the from the top side on these enolate, sorry, attack on this side from the top side is little bit hindered. Why? Because there is a upward directing propyl group. Now, if we look in comparatively the attack from the bottom side, what happened? The bottom side attack, there is no such steric hindrance because the bulkier group is on the top side. So the attack can take place very easily from the bottom side. So this can approach near to the this reaction center from the bottom side, and we get the product in which we can see here. So this group is directing downward. So basically this group has attached from the downside of this carbon center of this carbon center, right? So you can look at here. So this group is entirely on the downward, right? So this group is downward, and this is mainly governed by the stereochemistry present in the auxiliary part. And we can clue the chiral auxiliary. Let's say if you do the LiLH4, the base and H2O2. So what happened? Uh, in place of the LiOH, so this ester hydrolysis takes place. So we get here. So this bond get clued. OH get attached here, right? So this OH has OH negative attack here. So this bond get eliminated. Now what happened? We get the acid here and not here basically, because if you look closely, so this bond also, this amide bond and this N negative, that will be more stable compared to O and O negative and N, right? So this N negative takes place and followed by the N negative can abstract the proton. So basically there itself reaction takes place on O negative. So this is what acid we get. So in which you can see the new added group is on the downward directing. So which was literally impossible to convert this normal propionic acid to this type of stereoselective uh, this R2 methyl. It is impossible to prepare from this from the propionic acid to this R2 methyl 3 phenyl propionic acid. So that will be very easy by using such chiral auxiliary approach. So we get the asymmetric synthesis done uh, for this R2 methyl 3 phenyl propionic acid. Okay, so this is what we get in this chiral auxiliary. Uh, so this is the chiral auxiliary. In this case, this was our starting material, and this is our desired product. So I hope you can use this approach in if you have any a question comes on the synthesis, either on the retrosynthesis or the linear synthesis. So such approach you can use for such similar examples. Not necessarily the same example will come in front of you, but you can use the same methodology to solve such questions. Also, it is important to note here. So I mentioned here that Z inolate is getting formed as a major product. This is mainly because, so you can see this is the transition state occurs mainly because this transition state. If you look consider instead of here the hydrogen and the methyl here, so you can clearly see this and this, there will be a gauge conformation. They are in the not gauge you can say, but if the methyl will be here and hydrogen will be here, so in that case there will be the steric repulsion between this isopropyl and the methyl. Therefore, if you look as the if you keep the methyl group directing upward here in this case, so like this manner, so in that case what happen, this goes methyl group goes away from this directing bulk here isopropyl group. So this is how you can we have get here the Z inolate as a major product. Okay, I hope this you have get some idea about how the chiral auxiliary works. So if you look at the more and more example, then and then only you can able to uh, get habit of this chiral auxiliary, how we can use this chiral auxiliary in our synthesis. Now we'll look at the some other examples on the based on the similar chiral auxiliary approach. So this is again the same example. So in this case, if you can see the anticipating drug uh, molecule has been synthesized by using this chiral auxiliary approach. So in this case, again, the similar chiral auxiliary that we have used here, followed by, if you look at the starting material that we have, so this is, we have the alpha chloro acetic acid, and when you treat with the PCl5, it will give the acyl chloride. And similarly, this amide formation takes place with the chiral auxiliary part and the acyl chloride. Here you can see again, here the Z inlet formation takes place. Uh, in the same reaction, uh, the this group, the nucleophile, get attacks, substitute the chloride, right? So this chloride is substituted, and mainly this is basically a nucleophilic substitution reaction. So just the chloride is substituted with this group, and when you add the LDA and the ethyl iodide, then what we get here? We get here this product in which you can see this ethyl group has been directing upward. Why? Because the chiral auxiliary, we have in the chiral auxiliary this bulkier group which is directing downward, and that govern the attack of the new incoming, in this case the electrophile, which is coming from the upward. And when you do the hydrolysis of this amide by using the lithium hydroxide and the H2O2, what we get? We get our product here. So that's basically intermediate for the Leo tricetane molecule. And so the last step here, if you treat this acid with the ammonia, in that case, what we get? We get this desired product. So forget about the all other steps. But if you look closely here in the step, which I will highlight here. So this is the step, in this step particularly. So from here to here. So here the stereochemistry is mainly governed. And so the stereochemistry of the upcoming, in this case, the electrophile. So because of this thing, so when it form the enolate, so the attack of this electrophile takes place from the up top side, mainly because there is on the bottom side there is a bulkier group present in the chiral auxiliary part. So if you closely analyze all the example earlier I have shown and this example, so mainly the stereochemistry present in the auxiliary part is responsible for the stereochemistry in the uh, product. So when we want some, let's say in this case, if you want some opposite stereochemistry, so what we can basically choose? We can choose this chiral auxiliary. So if you choose this chiral auxiliary, which is in which this isopropyl group is directing upward. So in that case, what happens? In that case, what happened? The mainly the product formation has been takes place in the same manner in which the auxiliary, the stereochemistry is mainly directing by the auxiliary part. So basically the auxiliary part directing upward. So in that case, what happened? In that case, what we might get the product. So our products, in that case, what we will get? So we get this NH2, COO, and here this part which comes from the, so this ethyl group directing in that case will be directing downward. So this is how we can tune our stereochemistry, so based on the selection of the chiral auxiliary. So we can select appropriate chiral auxiliary to get the desired product. I hope it's clear up to now. So now we'll move to the some further some questions. Mainly, uh, similarly based on this carrier auxiliary, we'll see some examples of the carrier auxiliary. So this quantitative of the good carrier auxiliary is quantities of good qualities of good chiral auxiliary. So it needs to be available both in enantiomeric form. So why this is because so if we have selected one chiral auxiliary, so we if we have if it is available in both enantiomeric form, then we can basically in as I shown in the earlier example, if I select the chiral auxiliary with the different configuration, so earlier I have used the one yes chiral auxiliary earlier in the example I have used, but later what I have did I just simply did R chiral auxiliary and I changed the stereochemistry completely opposite. So if it is available in the both the enantiomer form, then that will be very easy depending upon our desired product whether we need the chiral compound, so the final compound, we can tune the uh, stereochemistry in the final product. So so based on this, we can select the chiral auxiliary. So therefore, it should be available and commercially available in the both the enantiomeric form. Secondly, needs to be easy and the quick synthesizable. So it should not be like the chiral auxiliary. It should not be very expensive or if it is not synthetically able to synthesize that chiral auxiliary, it will be very difficult. So it should be very quick and easy synthesis. So this is one of the chiral auxiliary, and you can see here so this is the S4 isopropyl 2 oxylidinone. So this can be synthesized in only two steps. The first step here is the BH3. So in the first step, we have this S-valine. So this is the natural amino acid, and this is basically a very cheap amino acid. If you do the carboxylic acid reduction with the BH3, THF, then we get the alcohol. And once we have this alcohol and the NH2 group in the starting material, and when you treat it with the diethyl carbonate. So what we get? We get this product, and this is basically our chiral auxiliary. So like this chiral auxiliary need to be easy and quick synthesizable. The third important parameter is you must have in the chiral auxiliary is the in it should be readily incorporated onto the a chiral substrate. So in this case, all the two examples that I have shown earlier, so the it was just the butyl lithium addition followed by the we can directly quickly add that chiral auxiliary on this carbonyl center. So this it should be very readily incorporated into the our chiral system. So this type of chiral auxiliary can be easily add to the across the chiral centers by using this just a coupling reaction. The either it is acid amide coupling or the esterification formation reactions. So the chiral auxiliary should be readily incorporated on the chiral. The quantities of chiral auxiliary, good chiral auxiliary. So sorry, qualities of another important parameter on the how the chiral auxiliary quality of chiral auxiliary will be. So it should be provide good level of asymmetric induction. So how it can be into provide good induction in the asymmetric induction mainly because in the form of enantiomeric excess. We will see this term what is enantiomeric excess is. Earlier also we have seen how this enantiomeric excess has been calculated in the some examples in the reaction. But yeah, so in our qualities of this good carboxylary, so the fourth parameter is it should provide a good level of asymmetric induction. So if you look at the carboxylary here, so because of this highly steric hindrance, we get this Z enolate formation selectively, followed by this when you do the reaction of this benzyl bromide on this enolate. So the benzyl bromide adds selectively on the downside, and why this is because mainly because of the steric hindrance on the auxiliary part. So this is how if we have the good quality, need a good quality chiral auxiliary. So in this case, the steric hindrance is the parameter which govern the stereochemistry or the asymmetric induction. So therefore, in such chiral we need to have a steric bulkiness as much as possible so as we can get high enantiomeric excess in this product formation, form product. So in this case, you can see this major product in this will be the CH2 pH group is directing downward. So that's what only the major product we are getting. So the another product, what is possible product here? So the possible product another is present here, which is this one in which this CH2 and the phenyl ring directing upward. But this is a minor product. The major product is see this one. And how the major product formation is mainly in this case governed mainly by this the stereochemistry present in the auxiliary part. So this is how we need to have a good level of asymmetric induction. This next sixth quality for the chiral auxiliary is the it needs to be selectively cleaved from the substrate. So as we seen in the earlier example also in this example, so you can see the first example that we have seen. So it can be very easily detached from the our substrate part. Sorry, our product. So in this case, we get this chiral substrate and we get the very selective formation of this product by because of this chiral auxiliary. Now it's time to remove the chiral auxiliary from the substrate and we need to detach this from the substrate. So if you just add the lithium hydroxide and the H2O2, so this chiral auxiliary which is from here, so we have very easily removed from the our product. So this is what our product was. We have removed this in only one step. So this also one of the parameter needs to be seen in the if you are selecting chiral auxiliary. Then and obviously if it is recoverable, then that will be one of the further advantage. We can reuse that one. So if it is reusable, then it will be again a good quality of this good chiral auxiliary. So in this case, if you look at here, so this is basically the one of the example of the chiral auxiliary, and this substrate is basically soluble in the organic solvent and can be separate uh, and the chiral auxiliary is recycled. However, the product what we have which is soluble in the water. So basically in this case, we can able to remove the substrate from the remove the chiral auxiliary from our farm product, right? So these are the some qualities of the good chiral auxiliary, and if you look at the more example of the chiral auxiliary, then you will more like examples based on this chiral auxiliary, then you will understand why I mentioned this why this good chiral the selection of the good chiral auxiliary is important. Now let's look at the terminology of this chiral auxiliary approach in the asymmetric synthesis. So asymmetric induction, as I have mentioned here one example, this asymmetric induction. So what is this asymmetric induction? We'll see that one in the detail. So it will be easy for your some since we are already moving in much more detail of this asymmetric synthesis. It's better to understand all these concepts in the asymmetric synthesis. So I have taken few concepts here, mainly which are we are going to use in day-to-day life of this in the asymmetric synthesis. Basically, the first important thing is the important term is the asymmetric induction. Uh, and if you look at the example that I have shown here, okay, so the example here, this step, this step involves the asymmetric induction. What is the asymmetric induction here? So basically, this incoming electrophile has been selectively attached to the substrate in the manner we get the selectively the subset comes here, which is directing uh, from the beta side, right? So mainly because which is directed mainly because of the this functional group or the group present in the chiral auxiliary. So this step was the asymmetric induction step. So asymmetric inductions refer to the control of selectivity extracted by the existing chiral center. And the existing chiral center in the example was this center was the existing chiral center. So each in all, if you look at this center, so this is basically existing chiral center. So the asymmetric induction has been just a second. Okay. So uh, we have so there was some disturbance here. So we are discussing here mainly the asymmetric induction. So this asymmetric induction refer to the control stereoselective uh, extracted by the existing chiral center on the formation of new chiral center. And in the example that I was showing, so if you look at this example, in the example, this was the center which is present in the auxiliary part, and the new center is going to create on this one. So this ethyl group has been is been added to this new center in the stereoselective manner. So basically, because of the steric hindrance in the auxiliary part, we are getting this ethyl group directing. Sorry, because of the steric hindrance of this auxiliary of this isopropyl group in the chiral auxiliary part, we are getting this ethyl group directing upward, and this step is the basically a steric induction step. And in this, the existing chiral center has been due to the existing chiral center, the stereochemistry has been uh, stereoselectivity has been formed across this center. So in this case, you can see selectively there will be ethyl group addition, which is mainly because of the stereochemistry present in the center in the auxiliary part. So that's what mentioned in this statement. So that's basically about the asymmetric induction. The next term we have used is the enantiomeric excess. So what is enantiomeric excess? So basically, this enantiomeric excess is refers to the excess of one of the enantiomer over the other generated in the enantioselective reaction. So because of in our reactions, because we have used the chiral auxiliary in this reaction, and here because of these steric hindrance present in the chiral auxiliary part, we are getting selectively the only one stereo center, sorry, the one product in which the stereo chemistry is fixed. The another product form here, which is minor product, so that we haven't mentioned here. However, the minor product will be like this, in which the So this is the entire R group, the bulky group that I will not draw here. However, the minor product will be like this CH3. So basically in the this minor product, so the stereochemistry of this one directing uh, downward. So that's the minor product, and this one is the major product. So basically this product is formed in the excess amount. So the in the enantiomeric excess, uh, so this represented in the example the in the quantitative manner in the form of enantiomeric excess. So if you want to calculate the enantiomeric excess, so basically this excess represent the efficiency of this enantioselectivity in the reaction. So higher is the enantiomeric excess, our reaction is highly enantioselective, that we can say. So this enantiomeric excess we can calculate it by, let's say the formation of the R product is measured, then the difference between these two product, the R and S. So in the example, so I will give the label. So this is basically the S product formation, S product, and this is, I just assigned the stereochemistry here. So this is the R product. So if you look at the enantiomeric excess, and I will give the random formation of the random yield. So this S product form in the 90% and this R product form in the 10%. So if you want to calculate the enantiomeric excess, so the enantiomeric excess basically the difference is like 90 minus 10 divided by the formation of the product. So basically that we have taken around 100% product formation takes place. So I have taken here the 10. So, and if you want in the percentage, so we can basically multiply with 100. So here 90 minus 8, it will be the 80 by 100 multiply by 100. Basically it will be a 80% enantiomeric excess, right? So in the example that I shown earlier, so the enantiomeric excess was 80%. Although formation of product is 90%, the major product formed here is the 90% this product. However, the enantiomeric excess of this stereoselective reaction was 80%. So this is the enantiomeric excess. So we have seen the asymmetric induction and we have seen the enantiomeric excess. So we'll see some advantage of this chiral auxiliary approach. So you can refer this advantage here. So I will not go in more detail for these advantages. I will just read that one and we'll see some problems based on this chiral auxiliary approach in the asymmetric synthesis. So the first advantage is the level of the facial control in the reaction are usually high, leading to high enantiomeric excess. So as mentioned, if you select the good chiral auxiliary, then we can get the high enantiomeric excess in the product, or we can get very higher selectivity, stereoselectivity in the product formation. Also, the diastereomers are generated from the use of chiral auxiliary can be separated over the conventional method, that is by column chromatography. So I have mentioned we can separate by, so if you have the major and minor product formation in let's take this example. So in this case, so the form, sorry, we are seeing this problem we are discussing. So in this case, you can see we are getting the one product major and minor. However, these two products are not enantiomers. They are the diastereomers of each other. And we know diastereomers can be separable by column chromatography. So diastereomers are totally different. So they have the different physical nature. Sorry, not physical, different physical natures, orientation, geometry, everything are different for the diastereomers, and therefore they can be separated by the normal column chromatography or the crystallization method. The third important advantage is the chiral auxiliary can be recycled, that I mentioned. We can basically recycle the chiral auxiliary. So we are also discuss here. So you can see if in this case, if you when this is the last step on the asymmetric synthesis using the chiral auxiliary. So I will just show where what it was the step. So you can see this was the last step here. So this is the example that we have seen earlier on the asymmetric synthesis. Up to here, the asymmetric synthesis has been done. Now it's time to remove the chiral auxiliary. So we have removed the chiral auxiliary, and we have used the H2O2, sorry, lithium hydroxide and H2O2. So what happened? So this auxiliary part has been eliminated or the removed from the our product. Now, since this media is the basic, it form in present in the form of sorry, carbonate form, and the carbonate, this basically the anion. This anion will be the water soluble. However, this will be soluble in organic solvent. Soluble in organic solvent. This is organic, and this cation anion, they are generally soluble in the aqueous media. So therefore, we can do the solvent extraction method after performing this reaction, and by this method, we can easily remove this chiral auxiliary part. So that's what I mentioned here. Advantage of using this chiral auxiliary, we can recycle this chiral auxiliary and reuse for further uh, different reaction. Now, another advantage is the sense of compression to the newly formed chiral center can be determined by X-ray crystallography. So, if you use the bulkier or the some rigid chiral auxiliary, the heavier one with having the some groups and all. So basically, the form product we can basically, if it is from the crystals, so then it will be very easy to determine the compression by using the crystallography. That's generally not generally case in case of enantiomers. But since in the chiral, when you use the chiral auxiliary, the form products are the diastereomers. So that computation of the newly formed chiral center, so it will be easy to determined by the X-ray crystallography. However, there are certain disadvantages of this chiral auxiliary method, mainly because two additional steps that we need to do. One first step was the addition of the chiral auxiliary to the starting material, and then removal of the chiral auxiliary part from the uh, our form product. So the two additional steps are required. That one of the disadvantage. The another disadvantage is the sometime having both enantiomers in the chiral auxiliary are usually uh, not readily available or expensive. Further chiral auxiliary need to be synthesized. In most of cases, I've shown when I have shown here. So the synthesis I have shown for the chiral auxiliary. So you can see. So sometime we need to really synthesize these chiral auxiliary parts. So this is how the auxiliary is synthesized here. So this is the chiral auxiliary part, and this can be synthesized. Although the synthesis is easy, however, that we need to synthesize. Then, as with the protecting group, the extra steps associated with the use of chiral auxiliary are required. Why? Because I shown in the last example here, we are using somewhat harsh condition to remove the chiral auxiliary. Here, you can see the LiLH, sorry, lithium hydroxide and the water, sorry, H2O2 we need to use to remove this chiral auxiliary from the target molecule. So, if one of the group in our product is not compatible with this, let's say in place of the H2O2 or not compatible with the lithium hydroxide, in that case, we cannot use this type of chiral auxiliary. So that's what, so additional, we need to either protect our group, functional group from our substrate, or we need to use some different chiral auxiliary. So that's the one of the concern with the use of this chiral auxiliary. And again, we need to use this chiral auxiliary in the stoichiometric amount. Why? Because we need to completely convert our startings to the uh, with the modified starting material by using the chiral auxiliary. So I just shown the example. So you can see here. So in this case, what we have did, we have converted all our starting to the this form, right? So basically, and to convert this entire starting material to this form, we need to use this chiral auxiliary in equal amount of our starting. So we are using 10 moles of the starting material. Then chiral auxiliary also we need to use the 10 mole. So the stoichiometry compound usage of this chiral auxiliary is required. So that's again one of the drawback or the disadvantage of this chiral auxiliary. So this is about the introduction about the chiral auxiliary. So when we are seeing some example, then it will be easy to understand how the chiral auxiliary works. So the main examples are fall in the category of this enolate chemistry and the use of this proline based uh, chiral auxiliary in the enolate chemistry. So that part are generally comes in the category of this chiral auxiliary approach in the asymmetric synthesis. So this is one example that I have shown. So if you look closely at this example, so this is basically, so this is the aldehyde and this is the ketone. When we treat the ketone with the base, what happen? It form the enolate, and when it form enolate, when you treat the enolate with the aldehyde, it forms the aldol condensation reaction, right? So this is the very well-known example, well-known reaction. So now it's just a modification. So we need the chirality in the product. So what happened here? So when we treat this compound with the, let's say, let's take the example of this proline. With this proline, what happened? This ketone and the proline, initially when you react this proline and the ketone, so it will form basically imine, right? So this is the CH3 and the CH3 imine, and in place of the base, obviously it will form the enolate. So this will be the N, right? So this is how it will. So up to here it was the positive charge, right? Right. So this will form this type of enamine, right? So this was the imine and this is the enamine. So once this enamine form, when you treat this with the aldehyde, so let's say this is the aldehyde. So the lone pair on this one goes here. The attack takes place on this carbonyl center, and we are getting the product. So the product will be. So I will write down that one the product. So the product is. So this is what product we get, and again, so we can basically. So this is what product we get. So this alcohol and so the stereochemistry of this hydroxy group of this alcohol is governed by the stereochemistry present in the this catalyst, whether it is LS proline or any other modified catalyst. So depending upon this catalyst, the stereochemistry is formed. So this basically later, so when it form, it can goes here. And when you do the again hydrolysis, I will just directly write down. It will be this will be R. So do you guys have any doubt on this reaction? If you have doubt, I will go step by step mechanism of this imine formation, followed by the enamine formation, and then attack of the enamine on the aldehyde to get this type of again imine, followed by hydrolysis, get the ketone back, right? And this basically hydroxy group is formed. So we are focusing on the stereochemistry of this hydroxy group. So how the stereochemistry looks like for this hydroxy group. So I hope for this enamine chemistry you don't have any doubt. So main concern here, the stereochemistry part of this. So if you look at here, the stereochemistry of this group. So when the attacks of this enamine takes place on the aldehyde, so this attack takes place. This attack not takes place in any random manner. It will takes place in selective manner. Why? Because there is a huge steric bulk of the present because of this group. So this group is directing upward, right? That I have mentioned here. So since this group directing upward, so the attack from the on this, so this incoming electrophile cannot takes place from uh, upper side. So it should be come from the down bottom side. So therefore it attacks on this one, and we get here in this case the selectivity in the this hydroxy group formation. Now, depending upon the selectivity of the product, so what we get, so this S-proline, if you use this S-proline, we are getting this hydroxy group directing in this manner. However, if we use some modified version of this, so the first one molecule that I used here, so with the first molecule, we are getting this product as a major product with the yield 68% yield and enantiomeric excess, which is 76%. So basically, among this 68% product formation, 76% is the enantiomeric excess. So how much percent of this isomer is formed? So if you just do the back calculation, so the 76, 100 minus 76, it will be 24. So 12, so 76 plus 12. So the 88% of the among the formed product. So 88% this isomer is formed plus 12% another isomers is formed. So 12%. So this is the percentage that I have mentioned the among this yield. So among this 68%, 88% of this product is formed and 12% of this product is formed. Don't be confused in between the yields and the enantiomeric excess. So this is how the enantiomeric excess that I'm has been mentioned here. So the 76%. So therefore the formation of product is 88% and this product form is the 12%, another isomer. And about the regarding the auxiliary, so this is the basically the auxiliary, the chiral auxiliary. So the stereochemistry present in the auxiliary part governs the formation of the or the induce the do the steric induction or the do the formation of the product accordingly. So if we have the similarly instead of S-proline, if we have R-proline, in that case what will happen? So in that case, this ratio will be somewhat different, right? Will be opposite. So instead of S-proline, let's say, if I use the R-proline, then what happen? So this COH basically will be in that case directing downward. And in that case, the product in which the OH group directing downward will be the major product. So this is basically vice versa, depend upon which chiral auxiliary we are using. If you use the another isomer or the enantiomer of the chiral auxiliary, so we get the opposite product formation. Right. So got some idea about the auxiliary, what is how this auxiliary works? This is the mechanism that I was talking about for this inolate formation chemistry. Sorry, not inolate, imine enamine mechanism. If I just look at the go by step by step. So the first step was the imine formation. So this imine is formed. Once this imine form, it forms this such cyclic six-membered transition states. And when this aldehyde, so if we look at this aldehyde, C double O H, this is the CH3. So this is basically the aldehyde. And in this one, This aldehyde form the, if you look at here, the hydrogen bonding with the carbonyl group, and that gives the formation of the syn product. Okay, I forgot to mention here in the last step. So if I have mentioned here, attack on the attack of this electrophile not takes place from the side of this group, of the bulkier group. So since I have the COOH group, that is the uh, acid group, in that case, it will be opposite, mainly because of this hydrogen bonding. And if you look at the product that I have here, the product in this case also, the product has the syn stereochemistry. So here, so if you look at goes here up to here, the product has the same stereochemistry as the our auxiliary part. This is mainly because of this hydrogen bonding. And if hydrogen bonding was not, if you uh, eliminate the effect of the hydrogen bonding, let's say if you just add this bulkier group, that is as in our earlier examples of this isopropyl, in that case, this product will be major if it is a only isopropyl group. So this is how the reaction mechanism works for this hydrogen bonding case. So we get the syn stereochemistry of the auxiliary here, which is, can you see here? Not here. Okay, they have just written the flip molecule. So this we, in our case, we are writing the molecule, the acid, so the ketone part. Here also the ketone part on the left side. So that's why. But anyway, at least you can get some idea about how this auxiliary affect the stereochemistry. So this is the third parameter that comes from our asymmetric synthesis. The first that we have already seen, which is the resolution method. The second one was the chiral pull approach, and the third one is the chiral auxiliary. So these are the some three approach used in the chiral asymmetric synthesis. I have given some a little bit introductions on the all of these approaches in the last lectures. And the last lecture we have seen the resolution and the chiral pool synthesis. In today's lecture, we have covered some of the examples of the chiral pool synthesis. So this is the first example that we have seen. This is the second example that we have seen regarding the chiral pool synthesis. Then this is the similar example which in all the chiral pool synthesis along with the some functional group interconversion. And then we have covered about the chiral auxiliary, in which we have seen how this what is chiral auxiliary, then how the chiral auxiliary works actually. We have seen some examples just to understand uh, where we are generally using this chiral auxiliary. So these are the some examples which involve the usage of this chiral auxiliary. So in which you can see in the first examples that we have seen. So we have the propionic acid as a starting material, but we want this R 3-methyl 3-propionic acid, 3-methyl 3-phenyl propionic acid. So this basically group we want to add at this center. So in that case, we have used this chiral auxiliary approach. So in which you can see on this propionic acid, we have converted this propionic acid to the cell chloride, followed by we have attached this chiral auxiliary to our starting material. Right. So you can see this was our starting material. We have attached this entire chiral auxiliary on this one. and then we did the reaction. So the LDA, when you add the LDA, it formed the Z enolate as a major product because of these transition states, followed by uh, steric, sorry, what we have seen, followed by asymmetric induction step. So that step, basically the attack of this attack on this electrophile takes place based on the uh, stereochemistry of these present in the chiral auxiliary part, mainly for this bulkier steric hindrance created by the bulkier group attached on the chiral auxiliary govern the stereochemistry in the product, right? So in this case, it is the steric group attack, sterically bulky group attached on the upward side. So therefore, our electrophile comes from the downward side, and this is what we get the product. And the last step was the removal of the auxiliary from the our target molecule. So we have removed this entire chiral auxiliary part. So this entire chiral auxiliary part that we have removed from the our substrate or the sorry our target molecule, and we get our target molecule. So which is the 3-methyl 3-propionic acid, 3-phenyl propionic acid, and we have recovered back this chiral auxiliary. So this is about the chiral auxiliary. I hope you at least got some idea about the how this chiral auxiliary works. So if you guys have any doubt, please let me know. I will cover that one.
Hello, sir. Hello.
Uh, yes, please, yes, please.
Am I audible? Good
Yes, you
evening,
are
sir. Actually,
audible. Sorry, you are mute right now. Can you unmute and ask me if you have any doubt?
sir, if you again summarize today's lecture, that will helpful for me, if possible for you.
Yeah, yeah, it is possible. It is possible. I
Actually,
will
I'm
quickly
late.
sum.
It's my
Yeah.
difficulties to. I want to attend your class, but when I reach it, already become 7 o'clock every day. That's why I missed.
Uh,
Otherwise, I have holiday. Then it's right. Okay, I joined it within time, but.
no issue. I will just quickly
If
summarize.
possible has please quickly एक बार
Yeah.
summarize.
I will spend 10 minutes on the asymmetric this part. So we'll start from actually, this is mainly because this part is one of the important part, and at least who are attending the lecture, at least they should know what we are really looking in this different approaches in the chiral synthesis. So I will just start from the, I think I have taken some example on the resolution also in the last week. I hope that examples on the resolution are clear. I will just quickly share this thing. Okay, so we were up to here in the last week. So in the last week, what we have did already, we were looking at the how this asymmetric synthesis has been achieved in the our routine organic synthesis. We know how the organic synthesis is done, but asymmetric synthesis is somewhat different because we need enantiomerically pure molecules in the our synthesis. So why it is important that we already know, because we have seen some examples. So mainly in this asymmetric synthesis, there are three different approaches or the three different strategy to get the asymmetric for this asymmetric synthesis. The we are going some reverse manner. So we have look first the resolution method, then the chiral pool, and the third one is the chiral auxiliary. So in the resolution method, what we can do, we can do some approach in which I shown one example here. So this is the one example. Uh, okay, this is the one example. So in the resolution, what we can do, we can convert our starting material to the some diastereomers. So that can be done by using either by adding some another by adding some other reaction on the substrate. So this is the first example that we have seen. So mainly in this example resolution method, I hope you can able to see. So this is basically our one of the starting, and we have performed, let's say, XYZ one reaction on this one, and we are getting the product in which you can see this B group is directing upward, and A. So this is the in the first case B group directing upward, and in this case B group directing downward. So this is the normal reaction. So in this, you we haven't did any stereospecific or stereoselective reaction. So in this case, what we are getting two different products. So one is the X that I have labeled, and another is Y. And these are the enantiomers. And we know enantiomers are not separable by normal column chromatography. So in the resolution method, the approach is either we can do the purification on the chiral column. In the chiral column, what happened? The column itself has the stationary phase in the column itself has the some chiral centers. So depending upon the stationary phase, so stationary phase interact differently with the different enantiomers, because one is the in one enantiomer. This, let's say, if you look at focus on the B group, so the B group directing upward. However, in the another enantiomer, B group directing downward. So the stationary phase react to differently on these two enantiomers, and therefore we are getting separation in the chiral column. So these two both enantiomers we can able to separate from each other by the chiral chromatography. Okay, so this is the first method for the in the resolution. So it's okay. The second one is the what we can do. So the purification is one of the method by we can directly do the chiral column. So that's one. Another what we can do, we can do one thing. We can add some reagent on this substrate. So let's take example. So what we can do, I have these two enantiomers in my mixture. If you add this one reagent, so if you add the reagent to the mixture of this, so this is entirely in mixture form, and if I add this reagent, so to this mixture, what we can get, we are getting these two type of different uh, salts. So basically, this is the this react with these S isomers as well as the R isomers. However, depending upon these two products are the different physical natures. So one of the salt that is with the R isomer. So in this case, this R and S I label directly it as the R isomer. So with the R isomer, it forms the crystalline salt. However, with the S isomer, it doesn't form the uh, crystalline salt. So this salt is soluble. However, the salt with the R is crystalline and insoluble. So this crystalline insoluble salt we can separate from the another one by just by the filtration method. So this is how we can do the resolution method. This is the second. We can do add some other reagent and make them able to separate from one another. So this is about the resolution method. The second method is the chiral pool. So in the chiral pool, what we can do, we can select the some starting material which itself has some chiral center, and we are carrying that chiral center till our end of the our product. So we'll when we see some example, then only we can able to uh, understand how this chiral pool synthesis generally done. So this is the simple example first, focused on this chiral center. So what is configuration of this chiral center? Sorry. So if you look at the configuration of this chiral center, so which is 1, 2, 3. This is the R chiral center, right? So this R chiral center, this focused on this one. So we have did a series of reaction. The first step is just the mesytyl protection. We just did the O mesytyl here, and it will be occurs here as well. The second step is since this is methanol, so this is basically the methanol goes attack here. So why this mechanism that I have shown how this works. Basically, the lone pair on this one goes here, and that helps to that forms some sort of when there is OMES complex is formed after, oh sorry, this H3O plus also there, right? So because of this acid, so this OH2 plus takes place. This lone pair present here goes here. This entire group is eliminated. It forms some sort of like this ketone type of structure, right? There is one hydrogen also, right? Like this structure, and the methanol is present. So methanol attacks here back again, and this back goes back because there was a positive charge, right? So like this, the methanol addition takes place here. So this will be OME. Here Mesitile, here also mesitile. Now, when you add the K and the Ran nickel, the mesitile group convert into the methyl group directly. So this is what happened in this reaction condition. I asked you to find out the mechanism of this reaction. Okay. Anyway, we are getting this product. Then the next step is the hydrolysis of this OME. So this OME get converted into OH, followed by basically these groups goes here. OH got eliminated, and this entire group. Oh, sorry, not like this. I just shown opposite manner. So this lone pair goes here. This bond goes here. So this is basically the part comes from these entire stuffs, right? So this is uh, this is what we get in this step. And later, when you do the Wittig reaction, so this Wittig reaction occurs on the some this aldehyde center. So that's no, not much concerning. So basically, here you can see this chiral center has been retained till the end, and this is what our desired product was. So in the synthesis of this product, which approach is used? So this chiral pool approach is used in the synthesis. So another example of similar manner. So chiral pool is basically pulling the reaction center or chiral center from the starting till the end. So this is another example. You can see. So in this chiral pool synthesis, you can see here, this is the L-serine, which is a natural enantiomeric available in the natural enantiomeric form, and it is very cheap. However, if you want to synthesize, this is the L-glyceraldehyde. This is the unnatural uh, stereo center. And if you want to synthesize this one, it is L-glyceraldehyde, R-glyceraldehyde, sorry, D-glyceraldehyde is commercially available. Oh, sorry, it is naturally available. However, D-glyceraldehyde is unnatural and it is very expensive. If you want to synthesize that one, so what you can do, you can select this S-serine. This is the natural amino acid and it is very cheap since it is natural, right? We can convert this S-serine to the this NaNO2 plus HCl. We can convert this NH2 group to hydroxy group followed by the acetone. So 1,3 diol protection we can do with this acetone. That's what, sorry, 1,2 diol protection we have did with the acetone. Then the BH3 LiLH4. So basically we did the acid reduction, acid converted into alcohol. Then again we did the PCC oxidation. So this primary alcohol converted into the aldehyde, right? And then followed by the aldehyde, the acetone deprotection. So this here the acetone protection, that step we have did deprotection step here. So and we got the L-glyceraldehyde as a which is the unnatural enantiomer of this carbide series. So that we can get here, right? So this is basically the synthesis has been achieved in this here from by using this chiral pool synthesis approach. So this is about the chiral pool synthesis. And the last step here in the asymmetric synthesis is the chiral auxiliary. That's what we have seen today. What is chiral auxiliary? So in the today's session, we have seen about the chiral auxiliary mainly. Okay, so the last method in the asymmetric synthesis is the uh, chiral auxiliary. So what is chiral auxiliary? So this chiral auxiliary is basically it is a chiral molecular unit that can be temporarily incorporated in the chiral substrate. So the chiral unit temporarily incorporated into the achiral substrate to guide the selectivity formation of one of the possible pair of enantiomers. So I will let you understand this statement. What is this mean? So when we look at the one of the example here, then you will easily understand what is this chiral auxiliary. So based on this one example only, you can able to very quickly understand. Okay. So auxiliary means the temporary unit we can incorporate to the our achiral substrate. So what we have substrate, we have this starting material. We want to not this. I should take the another example instead of this one. I will take the simple example first. So I have the this achiral unit, achiral starting material, the propionic acid. We want to synthesize the from this propionic acid. We want this target molecule. This is our target molecule, right? We want this synthesis of this target molecule. Then how we can do this synthesis? So basically, we can add the chiral auxiliary on this propionic acid, the starting material. How we can add? So we have the acid center. We can convert that to the acyl chloride and add this chiral auxiliary. So this is the chiral unit. What I have mentioned in the chiral auxiliary, the chiral auxiliary is basically a chiral molecular unit. Chiral molecular unit that can be temporarily incorporated to the achiral substrate. So this is the achiral substrate, and this is the chiral unit. We have incorporated that chiral unit temporarily on this substrate. Okay. So now when you do the reaction, inlet formation of on this substrate, on here, this intermediate one, what happen? We get the this Z inolate selectively. Why? Because of this sterically bulkier group. If you look at the transition state, so this methyl group directing away from the this bulkier group, and Z group formation, Z unit formation takes place in this case. Also, once this Z unit form, what happen? The now the addition of this electrophile. So this is the electrophile, and if you look at the here, when it goes down, either attack from the top side or attack from the bottom side. These two are possibility, right? Attack can be takes place from the upper side or the down side. So upper side attack takes place, let's say, but there is a problem. If you do the attack on the upper side, this because of the steric bulkiness, this electrophile cannot be comes in vicinity to the this reaction center. However, if you perform the attack in which the attack on the bottom side on the electrophile, so it is feasible because there is no such steric bulkiness there. So therefore, this incoming electrophile is now directing downward. And this is what here we have did the steric induction or asymmetric induction that we have did here, or the chirality induction on this chiral center, or also we can say selective addition of electrophile on this carbonyl center that has been done. Why? Because of this chiral auxiliary. And then, as mentioned earlier also, this is temporarily unit. So we don't want that one in the target molecule, right? So it should be able to, so this is temporal unit, and we can basically remove that unit. So this is basically the unit that we can remove. So we can remove this entire auxiliary unit. So this is not the part of our target molecule. So if you look at the target molecule, it is not part. So we can do the LiLH4, sorry, lithium hydroxide and the H2O2 reaction on this center. And what happened? So this amide bond can be cleaved in this step. So this amide has been cleaved, and we get this chiral auxiliary back that we can recover, and we get our target molecule also. So this is our target molecule. We have just basically removed the chiral auxiliary from the substrate. So this is about the chiral auxiliary approach in the asymmetric synthesis. So I hope it is clear now. So the three methods in the asymmetric synthesis. First one is the resolution. In the resolution, we are trying to find new method of purification of the enantiomers. So that's the one method. Reaction itself not be selective in the resolution. We are trying to resolve the two enantiomers from each other, right? So that's the resolution method. Second one is the chiral pull. So in the chiral pull, we select the substrate in such a way that that substrate, the stereochemistry present in the starting material, that has been carried till the end of the product, and that has been where that will be in the product also. So that stereo center we have written till the product. So that will be chiral pull, and chiral auxiliary is some additional unit that we can incorporate temporarily. And because of this temporary chiral unit, that is basically the chiral auxiliary, the reaction occurs stereoselectively. So here you can see this, the reaction takes place stereoselectively here. Why? Because of the this step has been done stereoselectively because of the chiral auxiliary. So this is where the use of this chiral auxiliary, and these are the three methods. So I hope it is clear now. So we'll see some common problems, maybe the synthesis problem based on these chiral pull as well as chiral auxiliary methods, maybe in the next video. Up to here, it is, I think it should be okay right now, right?
Thank you, sir. Thank you.
Okay, so these are the three approaches. I will upload the PPT in the Google Drive there, and you can refer the PPT, so it will be easy for you to understand. So we'll stop here for today, and maybe we'll back again with the same asymmetric synthesis problem in the next video. And we need to see the retrosynthetic problem on this asymmetric synthesis as well, because we are till now we are just saying the linear synthesis, but our topic is retrosynthesis, so we need to cover some retrosynthesis as well. Okay, so we'll stop here for today and see you guys on next Tuesday.